Lesson 5.1, Graphing Cubic Functions. Essential question. How are the graphs of f of x equals a times x minus h cubed plus k and f of x equals 1 over b times x minus h cubed plus k related to the graph of f of x equals x cubed? They are translations of the parent graph I'm not writing very well, of the parent graph f of x equals x cubed. Explore 1. Graphing and analyzing f of x equals x cubed. You know that a quadratic function has the standard form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. Similarly, a cubic function has a standard form f of x equals ax cubed plus bx squared plus cx plus d, where a, b, c, and d are all real numbers. A is not equal to 0. You can use the basic cubic function f of x equals x cubed as a parent function for a family of cubic functions related through the transformation of the graph of f of x equals x cubed. Complete the ordered pairs. So let's see here. Negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. Complete the table. Graph the ordered pairs. So negative 2, negative 8 is here. Negative 1 is here. 0, 0 is there. 1, 1 is there. And then 2, 8 is right here. And it graphs something like this right here. Kind of slid off there a little bit. And then it goes I'm not doing it right here. 2, 8. Let's see. Maybe I need to do it like this. That's a little bit better. And then, of course, that comes down more like that right there. And then it goes. And there you go. Let's use the graph to analyze the function and complete the table. Well, the domain is all real numbers. And the range is all real numbers. And the end behavior as x gets over here and approaches positive infinity, f of x approaches positive infinity. It gets way high. As x approaches as it gets down here, as it approaches negative infinity, f of x approaches negative infinity. Zeros of the function, x equals 0. Where the function has positive values is when x is greater than 0. Where the function has negative values is when x is less than 0. Where the function is increasing, the function increases throughout its domain. The function increases throughout its domain. Where the function is decreasing, the function never decreases, And is a function even or odd? It is odd. Odd because the cube of x equals negative x cubed. Okay? And think about it. If you put negative 2 in there and you cubed it, it gives you negative 2 cubed. They equal the same. That equals negative 8, and that equals negative 8. All right, good, good. All right, let's see here. How would you characterize the rate of change on the function on the intervals -1 to 0 and 0 to 1? Let's see here. Compared with the rate of change on the intervals -2 to -1 and 1 to 2. Explain. Well, let's go back and look at this. All right, what happens on the interval 0 or -1 to 0? -1 to 0. That is -1 to 0. That's right there. That's that it. So right there. All right. And then from 0 to 1, that's right there. So here's that right there. Okay. All right. Now, what about the range, or what about from -2 to -1? What about from here? What's the rate of change from there? And if you look, that's this spot right here. What's the rate of change there? All right. What's that rate of change? And from 1 to 2, that's this right here. What's the rate of change of this right here? Okay. What is the rate of change? Well, it is positive in all four because the function is increasing. From left to right, it's increasing, and it is much less. This area here, the rate of change in this area here is much less than the rate of change in this area here or this area here. Okay. That's a much, much, much steeper rate of change. Think about it. From here to here, it goes up by 1, but from here to here, it goes up by 7. Okay. So let's put that into words. Let's see. The rate of change on all four intervals, the rate of change on all four intervals is positive. Because the function is increasing. Is positive because the function is increasing from left to right. Now, what else? However, the rate of change, the rate of change on the interval -1, 0, and 0, 1 is much less than the rate of change on the intervals and on the intervals on both places, -2 to -1 and 1 to 2, because the graph rises more slowly. Slowly on the intervals. -1 to 0 and 0 to 1 than it does on the intervals. -2 to -1 and 1 to 2. Now, if I remember right, these had a rate of change of 7, and this had a rate of change of 1, okay, or slope of 1, and they had a slope of 7. Number 2, a graph is said to be symmetric about the origin, and the origin is called the graph's point of symmetry if for every point xy on the graph, the point -x -y is also on the graph. Well, let's take a look at that. So we got this point, we can say this point here, that's 2, 8. Is there a point -2, -8? There is. -2, negative. And the same thing right here. You got this point right here. This is -1, -1. And you got that point there, 1, 1. So we can say that yes, because for every point for every point xy equals, and we'll say x cubed, which is y, on the graph of the function, the point -x and then -x cubed equals -x cubed equals -x y is also on the graph. And remember that 2, 8, that's really 2 cubed, right? Well, you had -2, -8, which is really -2 cubed. And you could also say that's -2 and then -2 cubed. Okay, they all three equal the same. So let's look at number 3. The graph of g of x equals -x cubed is a reflection of the graph of f of x equals x across the y-axis, while the graph of h of x equals -x cubed is a reflection of the graph of f of x equals x cubed across the x-axis. If you graph g of x and h of x on a graphing calculator, what do you notice? Well, let's try that. So let's go to graphs here, and we'll graph x cubed, and there it is. Now, the second one was g of x is -x cubed inside. So let's and then open parentheses, -x, close parentheses, caret 3. All right. Now, let's try the third one. -x cubed, okay? And look, see how those two are right on top of each other. Those two are right on top of each other. So what do we notice? What do we notice? The graphs of g of x and h of x, the graphs of g of x and h of x are the same. They are the same because f of x is an odd function that is f of negative x equals negative f of x, given that g of x equals f of negative x and h of x equals negative f of x, you have g of x equals h of x. All right. What that's saying is, given that g of x is negative x cubed equals negative x cubed. All right, that's what that's saying. All right. Graphing combined transformations. When graphing transformations of f of x equals x cubed, it helps to consider the effect of the transformations on the three reference points of on the graph of f of x equals -1, -1, 0, 0, and 1, 1. Now let's go back to this. All right, let's go back to this. And then tab, and we'll get rid of that one. And we'll go up and we'll get rid of that one. And now let's press enter. I'll try to get rid of both of them. Let's see here. Let's press tab and let's see what do we got. That one's gone. Oh, that one stayed. Let's see if that's gone now. All right, good. Now, if you'll look, it goes through 1, 1 right here. It goes through 1, 1 right there. And it also goes through -1, -1 right there. And easy thing to do, press Control T for table. And if you look, 1, 1, and then scroll up there, -1, -1. Okay? So all of them, the parent graph has -1, -1, 0, 0, and 1, 1. It goes through those points, which that makes the transformations easy. Okay? So -1, -1, it becomes -b plus h and -a plus k. 0, 0 is just h and k, and 1, 1 is b plus h and a plus k. That makes finding the transformations much easier. Identify the transformation of the graph of f of x equals x cubed that produce the graph of the given function g of x. The graph g of x on the same coordinate plane as the graph of f of x, or then graph g of x on the same coordinate plane as the graph of f of x by applying the transformations to the reference points -1, -1, 0, 0, and 1, 1. So g of x equals, or a, I'll let you do a, and then when you come back, we'll do b together, okay? And I need, let's see, that's too big. Let's see, 150, does that get that? Yeah, that gets that all on one page that we can see the whole thing. Okay. So let's identify some stuff. Okay, this is the B. Okay, that's the B. Now, let's see. How was that supposed to be? Remember back in the thing, it said 1 over b equals 2. So what is that going to make b? So b is going to equal 1/2 if you do the multiplication there. So that's the b. What is the h? The h is right here. This is the h. Okay, 3 is the h. That's the h. And then 4 is the k. That's the k. All right, the transformation of the graph of f of x that produce the graph of g of x are a horizontal compression by a factor of 1/2, and that's your b. All right, that's your b. A translation of 3 units left, that's your h, and 4 units up, that's your k. Okay, so we got this point, -1, -1 right here. So we're going to have 1/2 times -1 plus, and that was x plus 3. So that's going to make h -3. And that's going to give you -3 1/2. Okay, now what about the y? The y is going to be -1. That's that -1 right here. That's the -1. And this is that -1 right there. Okay, -1 plus k, which is 4. And then -1 plus 4 is -3. So that's going to give you a new ordered pair of -3 1/2, 3. So -3 1/2, -3 1/2. That's going to be out there. And then 3. -3 1/2, 3 is going to be about right there. Okay. Well, let's look at 0, 0. Oh, I hit that button. Dadgummit. How do I get that back? How do I get that back? I did not mean to do that. I'm not seeing. Oh, there it is. There's the bar. Okay. The next one, you're going to do the same thing. You got 1/2 times 0 plus -3, and that's going to give you -3. And then you got 0 plus 4, which is going to give you 4. So your next order pair is -3, 4. So let's find -3, and then 4 is going to be right there. Okay? And we'll do the third one. You have 1/2 times 1 plus -3, and that's going to give you -2.5. -2.5. And then 1 plus 4 is going to give you 5. So that gives us an ordered pair, -2.5, 5. So -2.5 and then 5 is going to be right there. So our graph is going to look something like this right here. Over a little bit too much. And like that. Okay, not the best graph in the world, but we can fix that. So we got -3, 4 right there, and that's right there, and that's right there. So let's try this. And then kind of like that. All right. Your turn. Identify the transformation of the graph of f of x equals x cubed that produce the given function g of x Then graph g of x on the same coordinate plane as the graph of f of x by applying the transformations to the reference points -1, 1, -1, -1, 0, 0, and 1, 1. So let's take a look out here. What do we got? What is A? This right here is A, and so we'll call that A equals -1/2. So that's going to be a vertical compression, a vertical compression by a factor of 1/2, or by a factor of 1/2, and a reflection across the x-axis. Next we have, well, we don't have a B in this one, but we have a K, or an H. H is 3. So H equals 3. And that's going to be a horizontal translation, 3 units right. Okay. I want you to note that the translation of 3 units to the right affects only the x coordinate, while the vertical compression by a factor of 1/2 and the reflection across the x-axis affect only the y coordinates. So here we've got -1, -1. Okay. Well, that's going to become, we don't have a B and we don't have a K. See, there's no, well, let's see here. That would be +0, so, and that would be K, and 1/1 for the B. So we got -1, that's going to be -1 plus 3. -1 plus 3. Let's see, I use red for that. Plus 3. Plus 3. And then you're going to have -1. Oh, what do we? We're multiplying by 1/2, -1/2. So we're going to have -1/2 times -1. And that's going to give us 2 and then 1/2. Okay, and that's positive. So let's find 2. 2 and 1/2 is going to be right there. Okay, and then we have 0, 0. And that's going to become 0 plus 3 and -1/2 times 0. And that's going to give you 3 zeros. So let's find 3 zeros, going to be right there. Okay. And then we have 1, 1. And that's going to become 1 plus 3. And you're going to have -1/2 times 1. And that's going to equal 4 and -1/2. So 4 and -1/2. And that's going to look something like this right here. And there we go. Getting better already. There we go. Now, we've got, let's go in here and let's do this. So we've got, what do we got? X cubed, right? X cubed, which is what this is. That's X cubed right there. So let's make it. Let's press tab, and we're going to have -1, control, divide 2, and it's going to be times, and then x minus 3, x minus 3, close parentheses, and then squared. Press enter. I said squared, and I should have put in cubed, caret 3. And there we go. And that looks like, well, kind of like what we did. Of course, this is a much more accurate graph than the one that I did, but shh, don't tell anybody. Writing equations for combined transformations of f of x equals x cubed. Given the graph of the transformed function g of x equals a times 1 over b times x minus h cubed plus k, you can determine the values of the parameters by using the same reference points that you used to graph g of x in the previous example. Example 2. A general equation for a cubic function g of x is given along with the function's graph. Write a specific equation by identifying the values of the parameters from the reference points shown on the graph. Now it's a party, okay? You do A, and then when you get back, we'll do B together. All right. So what do? They give us some points, okay? Now, are any of those points significant? Well, this here, that's that point of inflection or reflection or whatever, and symmetry, point of symmetry and whatnot. That gives you a couple of things. It gives you the H. It gives you the H. And it gives you the K. All right. So you know that H is -4 and K is -1. All right. So H is -4 and K is -1. Good job. Identify the value of B from either of the other two reference points. The rightmost reference points has general coordinates. Okay. So we got B plus H and then 1 plus K, right? Okay. Substitute -4 for H and 1 for K, and setting the general coordinates equal to the actual coordinates gives this result. B plus H and 1 plus 1 equals B minus 4 and 2. All right. 1 plus 1 is 2. So, and then you got B plus, and then H is -4, and that is supposed to equal -3.5, right? So this is really B minus 4, B minus 4. So we add 4 to both sides, and B equals, that would just be 1, or 0.5. We'll put 0.5, 0.5. All right, started out with a decimal, ended with a decimal. So here we go, 0.5. So now we know what B is. B is 0.5. Write the function using the values of the parameter and then simplify. So if B is 0.5, that would be 1 over 0.5, which is 2. So we're going to put 1 over 0.5 times x minus -4, and then cubed plus 1. Okay, so g of x equals, well, 1 divided by 0.5 is 2, and then that's x plus 4 cubed plus 1. And there you go. You've done it. It's not hard. It's not hard. Your turn. So a general equation for a cubic function g of x is given along with the function's graph. Write a specific equation for identifying the values of the parameter from the reference points shown on the graph. All right, so what do we got? Quiz, pop quiz. What is H and K? H and K. H and K. So that's K. So our vertex, or however you want to call it, we've got -2, -2. And maybe I should put those in there. -2, -2, and -2. All right, that's our H and our K. H, that's K, and that's H. Can't say that enough. Got to keep it. All right, so now remember the point. What was that? That point 1, 1 was supposed to be. What was that supposed to be? That was supposed to be H plus 1, and then A plus K. Okay, so that's going to be -2, -2 plus 1, and A, well, we don't really know what A is just yet, okay? So we'll say A plus, and then K is -2, so we'll just make that -2. Okay, so now we got that. Well, that's going to give us what? Well, what is it? What is this point here? This is -1, -1. So that's supposed to equal -1, 1. Okay, -1. So -2 plus 1, that gives you -1. And you go over here, A minus 2 equals 1. So let's add 2 to both sides. And so A equals 3. Okay, and what would we, so A equals 3. So A is 3. Okay, so now we can write our equation. G of x equals 3 times, and that's going to be x plus 2, and then -2. -2. Not a problem. Not too shabby at all. Not a problem. Look at this one here. So we got A equals 3. So we got over here, what is our H? H is 1. What is our K? K is -1. All right, we know that now. Now we've got, well, it says this time we're using B here, right? Or B. Now we're using B. Okay, so what do we know? B affects what? B affects the H, A affects the Y. So we're going to have, this time we're going to have B plus H, and then we're going to have 1 plus K. All right, 1 plus K. So we don't know what B is. Let's make B green. We don't know what B is, but we know that, well, what do we know? We know that B plus H will be plus 1, and we know that 1 plus, and then K is -1. All right, and we know that that is supposed to equal 5, 0. Okay, because that's what that says. That says 5, 0. So 1 plus -1 is 0, not a problem. B plus 1 equals 5. Subtract 1 from both sides, and you got B equals 4. Okay, so now we can write our equation. We have G of x equals, and that's 1 over B, which is 4, times and then you got x minus h, which is 1, and that's going to be cubed, and I didn't put a cube over there, minus 1, or plus k, which is negative 1, so minus 1. Looking good, looking good. Modeling with a transformation of f of x equals x cubed. You may be able to model a real-world situation that involves volume with a cubic function. Sometimes mass may also be involved in the problem. Mass and volume are related through density, which is defined as the object's mass per unit volume. If an object has mass m and volume v, then its density equals d equals mass divided by volume. You can rewrite the formula as mass equals density times volume to express mass in terms of density and volume. All right, so I'll let you read through A, and you can see how it's done, and then we'll do B together. Estimate the radius of a steel ball bearing with a mass of 75 grams and a density of 7.82 grams centimeters cubed. Let R represent the radius in centimeters of the ball bearing. The volume V in cubic centimeters of the ball bearing is volume equals, I have to give you that's going to be 4/3 pi r cubed. The mass m in grams of the ball bearing is mass of R equals 7.82 times the volume of R, which is 32.76. Okay? And so if the radius is 0, then the mass is 0. If the radius is 0.5, so 0.5 times 32.76 is, let's see here, 0.5, and that gives you 4.1. 1 gives you 32.76, and then 1.5 gives you 110.57, and 2 gives you 262.08. Okay, draw the graph of the mass function, recognizing that the graph is a vertical stretch of the graph of the parent cubic function by a factor of 7.82. 7.82. Then draw the horizontal line m equals 75, and estimate the value of R where the graphs intersect. The graphs intersect where R is approximately, okay, so let's draw. Well, we got 0, 0, right? And we got 0.5 and 4.1, that's going to be real low. 1 and 32.76, that's going to be maybe right there. 1.5 is going to be 110, and just under that. And then 2 is going to be 262, that's going to be maybe right there. And that's going to look something like this right here. And you want to, when you're doing these, you want to get them as close as you can to being just right. And if you can do that, you're better than me. That's 75. That's maybe right across there. And so we're looking at, this is going to be some point right here. So let's see. I wonder and let's see. Okay, so the graphs intersect at approximately, let's look at that, That's 1.2, probably about 1.3. So the radius of the steel ball bearing is about 1.3 centimeters. Discussion. Why is it important to plot multiple points on the graph of the volume function? Because you are using a graph to estimate the value. Because you are using the graph to estimate the value of the independent variable from a given value of the dependent variable. The graph should be as accurate as possible. All right, good, good. Okay, before we leave this, let's look at this. Let's take a look. This is kind of hard to do. It's kind of hard to do like that. What if we use the old calculator here? So what did we have? The volume was 32.76, and it said r cubed. Well, we'll have to use x, caret 3, and enter. There it is. And then the other one was, well, we wanted to know 75. Yeah, 75 grams. So let's say 75. Press enter. And let's roll up here real quick. And come on, there we're getting close. There. Oh, there it is. How about menu 6 forward, and then 1.32. What did we estimate on the other? 1.3. So that wasn't too bad. That wasn't too bad at all. All right. So let's see here. Let's go on to the next one. Your turn. Use a cubic function to model the situation and graph the function using calculated values of the function. Then use the graph to obtain an indicated estimate. Polystyrene beads fill a cube-shaped box with an effective density of 0.00076 kilograms a centimeter squared, which accounts for the space between the beads. The filled box weighs 6 kilograms, while the empty box weighs 1.5 kilograms. Estimate the inner edge length of the box. Okay, so what do we know? Well, we got 6 minus 1.5 equals 4.5 grams. So that's how much the beads, that's how much the beads are going to weigh, 4.5 kilograms. All right, now let's see. The volume of the length is length cubed, okay? And it said the mass was 0.00076. So our formula is going to be 0.00076 cubed, length cubed, okay? And we can make a table of values. Let's see, length, mass, 0, 0. And then if you put in 5, you're going to get 0.095. If you put in 10, we'll move it over a couple. you're going to get 0.76 and 15 will give you 2.565, and 20 will give you 6.08. So that gets us past 4.5. So we know our answer is going to be somewhere between 15 and 20. So the thing to do would be to go into our calculator. Let's go into our calculator. On, new document, no, and graphs. We're going to put in 0.00076 x cubed. Graph that. All right. And then we're going to press tab and put in 4.5. Okay. So let's take a look at that. And then menu 6, 4, and that's going to give us, it looks like 18.1. Well, we said based on our table, it would be somewhere between 15 and 18. So let's go back over here and we'll grab that. 0 zeros right there. 5 is going to be just barely above it. 10, 0.7, a little bit more than 3/4, not a whole lot. 15 is 2.6. 15 is 2.65, just over half. And then 20 is going to be 6.08. That's just barely above. And then we've got our line here at 4.5. And then let's see what we can do by here. All right. So this right here, that's 17.5. So this right here, and that's just 18.1. Okay. So the graphs intersect where L is approximately 18 centimeters. So the inner edge length of the box is about 18 centimeters. Identify which transformations, stretches or compressions, reflections and translations of f of x equals x cubed change the following attributes of the function. So the end behavior, what changes the end behavior? Let's see here. Reflections across the x-axis, reflections across the x-axis, and so that's a is less than 0. Reflections across the y-axis, across the y-axis, and that's going to be b is less than 0. Those two change the end behavior. Location of the point of symmetry, what changes that? Vertical translations, and that's where k is not equal to 0, and horizontal translations. And that's where h is not equal to 0. They changed the point of, change the point of symmetry. All right, symmetry about a point. Well, no transformations change the function symmetry about a point. None, not with the cubic function. Essential question check-in. Describe the transformations you must perform on a graph of f of x equals x cubed to obtain the graph of f of x equals a times x minus h cubed plus k. I may need a little room there. Let's see here. Let's see if we can close all that up. All right, just in case I need a little room. If A is less than 0, reflect the parent graph across. Reflect the parent graph across the x-axis. Then either stretch the graph vertically by a factor of A, if the absolute value of A is greater than 1, or compress the graph, the graph vertically by a factor of A, if the absolute value of A is less than 1. Finally, translate the graph H units horizontally, and that could be left or right. And K units vertically, and that would be up or down. All right. Great lesson, folks. See you tomorrow in class, and y'all have a good evening.